Nickel titanium, or nitinol, is an alloy that can change back to its original shape under high temperature after its deformation. It is used in glasses frames, braces, and self-bending spoons and magic acts. For this project, our group focused on nitinol 55. Nitinol is held by metallic bonding, which is formed by the sharing of free valence electrons between nuclei. This is why metallic bonds are considered strong, stable bonds. This can be accurately shown by the sea of electrons. Contemporarily, many studies have been conducted to replicate the characteristics of nitinol through the controlling of interatomic potentials, which create crystal and interfacial structures. The parent phase of nitinol is austenite with a primitive cubic crystal structure. The daughter phase is martensite with a monoclinic crystal structure. Nitinol is an interesting phase in that it is very elastic in response to stress. The martensite phase also has the ability to return to the parent phase upon heating and recover the shape of the object because martensite is able to undergo deformation without breaking atomic bonds. This twinning property of martensite allows for atomic plane rearrangement without causing permanent deformation or slip. Carbides and oxides can cause a formation of pinhole and pit-type defects on the nitinol surface, impacting the performance of nitinol as an SMA. Therefore, the vacuum arc remelting process is employed in the manufacturing process to prevent the carbon diffusing into the nitinol during melting. There are two critical points of the phase transformation of nitinol that can be attributed to its shape memory and elasticity properties. Heating nitinol above the transformation temperature, which ranges from 73 to 383 Kelvin, will revert the crystal structure to the austenite phase. Cooling the object will revert the crystal structure to the martensite phase. It is not possible for nitinol to be made into a single crystal, and it does not have to coexist with other phases because of its pure state. Nitinol is not a metastable phase because it is not an equilibrium phase. Unlike the transformation from diamond to graphite, rapid heating or cooling would be needed to change the phase of nitinol. Overall, the interesting shape memory and elasticity characteristics of nitinol can be understood through the study of its bonding, crystallography, defects, and phase diagrams.